3.8 Derivatives of inverse trig functions. So this is going to be a bit different than when we take derivatives of regular trig functions. First off, just to remind you, inverse trig functions are when we have this -1 power that we put in between sin and x for each of our trig functions. So this is the inverse sine of x, or another way of writing it is to write arc sine of x. And that's true for any of our trig functions, that we can write it either of those ways. And if I think back to what it meant to have inverse sine, that's where instead of looking for the sides of our triangle, we were looking for an angle. And if I go back and think about all of that stuff, and I look at my textbook or go to Google or whatever, you can see how all of these things, how we get all of these things. It has to do with setting up a triangle and using the Pythagorean theorem and all this different stuff. So I will tell you that these are the derivatives for our inverse trig functions, and then if you want to go and figure out how they come up with those, then you'd want to look for a different video or look in your textbook or something. So the way that these works is these are basically going to be formulas that we're going to fill in. So this says that the derivative of the inverse sine of u equals, what I do is I take whatever u is, which it can be just a letter like x, but most often it's going to be something that has more than just x, like 2x or something else. We're going to take the derivative of that and put it on top. And then on bottom, we're going to put the square root of 1 minus whatever this is squared. And then we'll simplify what we can. And so that's probably actually the trickiest part of this, is knowing how to simplify these after we've plugged everything in. So each of these has its own thing. If you're trying to memorize these, sine and cosine are similar, just sine is positive, cosine is negative. Tangent and cotangent are the same, just one is positive, one is negative. And the same for secant and cosecant. So there's some tricks to help you memorize them if your teacher is making you memorize them. So we're going to do some examples. And so my first example is going to be inverse sine of 2x, like what I mentioned a second ago. And so I went ahead and reposted what the formula is for that so that you can see it on the screen here. So what matters here is what u is. U is the inside of my inverse sine. So u is 2x. And then I need to figure out what that means u prime would be. So what is the derivative of 2x? It would just be 2. And so now I have the two things I need to fill this in. So my derivative, dy over dx, is going to equal, u prime is on top, so that's 2. And on bottom, I'm going to put square root of 1 minus u squared. It's really important that we put u in parentheses when we square it, because what's going to happen is both parts of this need to get squared. This isn't 2x squared. This ends up being 4x squared. So there's not actually much I can do to simplify this except for rewrite that so that this is 1 minus 4x squared. Now some people are going to be inclined to try to simplify the bottom of this with the square root. If this said 1 times 4x squared under our square root, yes, we could simplify that into 2x. But because it's a minus sign, what we're trying to figure out is two things that multiply together to get 1 minus 4x squared, which would be 1 minus 2x and 1 plus 2x. But the problem is those aren't the same, which means I can't take the square root of this, because I would have to have basically 1 minus 2x squared or 1 plus 2x squared, and I don't have those. So I can't simplify that square root, and it's better in general when in doubt to just assume you can't simplify a square root, because there's so many times where you can't, and it would be frowned upon for you to even try. So our answer to this is 2 over the square root of 1 minus 4x squared. Example 2 has inverse cosine of x cubed. I'm basically going to go through one of each type and show you just a little, like some of them are a little bit different than others because of what the formula is. So this is our u equals x cubed. So I need to find u prime, which will be 3x squared. So my derivative, dy over dx, equals, I put negative u prime on top, so negative 3x squared is on top, and on bottom I'm going to put the square root of 1 minus u squared. Now what happens here is I have x cubed squared, which that 3 is kind of hard to read. X cubed squared, so you might be wondering how to deal with that. It's the only thing that's going to change in our problem. And whenever I have something to a power, then another power right next to it, I multiply those together. So this is going to be 1 minus x to the 6th power, because 3 times 2 is 6. And I can't simplify this because I have a minus. I'm subtracting underneath my square root instead of multiplying. So that is my answer. Tangent. We have the square root of 3x as u, and so this actually is a little tricky as far as the derivative of u goes, because what we need to do is say, well, this is 3x to the 1/2 power, so u prime is going to require us to use the chain rule. I multiply by 1/2, I leave the inside alone, I subtract a power, and then I times by the derivative of the inside. The derivative of 3x is 3. So u prime is 3/2 3x to the negative 1/2. Now let's plug this into our formula. dy over dx equals, u prime is 3/2 3x to the negative 1/2 over 1 plus u squared, and there's not a square root this time, so 1 plus the square root of 3x squared. Now there's a couple things that we can do to this now. The square root of 3x squared, the square root and the squared will cancel each other out and give us just 3x. So it'll be 1 plus 3x on the bottom. But also there's some things that I can do with the top of this that, depending on your teacher, they may or may not care if you do this or not. But I definitely want to change this to 1 plus 3x. This 3/2 would actually end up being a 2 on the bottom, so that there's a 3 on top and a 2 on bottom. And then 3x to the negative 1/2, we could move down to the bottom and make it have a positive exponent. Not only would it have a positive exponent, when we did that, we would be able to change it back to a square root. So our answer to this would just have 3 on top, and would have, it doesn't necessarily matter the order you put this in, would have 2 square roots of 3x, and in parentheses 1 plus 3x. And I don't need to distribute or anything. I can just leave it like this for my answer. Example 4, cosecant. Inverse cosecant of 1 over x squared. So we're going to use this formula, which has more u's than the other ones we've dealt with are, but that's fine. Also, it has an absolute value, has some absolute value bars around u, which is important that you put those. It may not seem like it's a big deal, but this u that's on bottom is only allowed to be positive because of the way it's derived, and if you want to go look that up, you can. So u is 1 over x squared. To take the derivative of 1 over x squared, I need to think of that as x to the negative 2, assuming I want to avoid the quotient rule, which I know we all want to avoid the quotient rule. So u prime is going to be negative 2x to the negative 3rd, because I multiply by the power and then subtract 1, so it makes it more negative. So dy over dx equals negative 2x to the negative 3rd over negative 2x to negative, oh no, just kidding, that's supposed to be, oh no. Okay, don't worry, it's all fine. So u is in here, so this is x to the negative 2. And then square root of x to the negative 2 squared minus 1. Now, as far as simplifying goes, again, it kind of depends on your teacher. This could get really messy. I definitely want to change this to a positive 2x minus 3 on the top. But on bottom, all I'm going to do is change this x to the negative 2 squared to an x to the negative 4th. If you're not sure if you're allowed to take the absolute value bars off, then you wouldn't. And so I happen to know that this is 1 over x squared, and no matter what I plug in for x, I can't get a negative number, so I don't really need those absolute value bars. I can leave them off if I want to. It's better to be safe than sorry, though. So if you're ever not sure, you would want to leave the absolute value bars around it. Why did I just put them? I just said I didn't need them. All right, x to the negative 2. And then square root of x to the negative 4 minus 1. And that's where I would leave it. If we start changing all of these to bottoms of fractions, like 2 over x cubed, and then 1 over x squared, like, it's just going to look messier, and I'm not really going to end up necessarily being able to help a lot of this. I guess actually we could simplify this some, but don't worry about it unless you want to. That's fine is the answer. Example 5. Inverse secant of square root of 7x. So u is square root of 7x. U prime, we're going to have to switch this to 7x to the 1/2 and then chain rule. So u prime is 1/2 7x to the negative 1/2 times the derivative of the inside, which is 7. So if I rewrite that, that's going to be 7/2, 7x to the negative 1/2. So u prime is on top. 7/2 7x to the negative 1/2 over u, which is square root of 7x, inside of my absolute value bars, then square root of u squared, which our square root is 7x, so square root of 7x squared minus 1. Now, we're going to be able to do a number of things here. Like, I can move the 2 down to the bottom. I can move this whole thing to the bottom to give it a positive exponent. And then I don't actually need the absolute value bars around square root of 7x, because no matter what I plug in for x, I have a positive square root. So the only thing I'm going to end up with on top is 7. I'm going to move this down to the bottom so that this is the square root of 7x on the bottom. I'm going to get rid of these absolute value bars so that that is also square root of 7x. And then my square, inside my square root, the square root of 7x squared will cancel each other out, so that this is just 7x minus 1. So there's one more thing we can do. If I have square root of 7x times square root of 7x, that means that I have just 7x, and so my 7's can cancel. So this is 1 over x square roots of 7x minus 1 for my answer. Finally, cotangent of negative 4 over x to the 5th. We would start by saying that u is negative 4 over x to the 5th, which is really negative 4x to the negative 5th. U prime is the derivative of that, which is 20x to the negative 6th. I'm going to plug this in so that I get negative u prime, so negative 20x to the negative 6 over 1 plus u squared, so negative 4x to the negative 5th squared, all I'm going to do here is negative 20 x to the negative 6 over 1. If I square negative 4, I get plus 16, and this is x to the negative 10th. So what I did earlier where I was like, oh, that could cancel, we won't be able to cancel the same way on this one because of this plus sign on the bottom. Like, this is pretty much my answer. Even if I change these back to positive exponents, the problem is that this x to the negative 10th would only go underneath the 16. So maybe if I got common denominators and then divided, I could simplify more, but I don't want to do that. You can try it if you want to. So that is one each of our different kinds of inverse trig functions. So have a great day.